Okay. All right. So the general reaction scheme involves treatment of an alkene with dihydrogen gas and a catalyst. And the result is reduction of the pi bond to form the corresponding alkane. Okay. Very useful transformation because alkenes are sort of orthogonal in terms of their reactivity to a lot of functional groups. They're easy to make, and then ultimately you can reduce them to get an alkane. These hydrogenations are always catalyzed, so you add some reagent that helps to lower the activation energy for the transformation. And the catalysts are typically based on platinum or palladium. Although there are hundreds of different hydrogenation catalysts out there. When you're answering questions either on sapling or an exam setting, and you want to invoke hydrogenation, put down platinum or palladium. Don't just write catalyst, and H2, of course. We're not going to talk about the mechanism because the mechanism is complex. A lot of these catalysts are what we call heterogeneous, so they don't dissolve in solution, and that means that you have sort of an unusual but very interesting scenario where the alkene and the hydrogen are combining at the surface of these metals. There are also, there's a library's worth of literature on homogeneous hydrogenation catalysts that do dissolve, and those mechanisms are distinct. And so for the sake of not making this unnecessarily complicated, we're not going to discuss mechanism for this transformation. So okay. All right. So we're going to essentially talk about one new reaction today, which is oxymercuration-reduction. And then what I'd like to do is take a couple minutes and try and sort of highlight some of the commonalities of the reactions that we've discussed this far. Remember, I told you that the best way to learn this material is to learn it mechanistically, focus on mechanism. And the idea there is that when you aren't sure of the details, then the mechanism can guide you to the right answer or the right details. Okay, so we'll spend some time at the end of class on that. So all right, so oxymercuration reduction is transformation that allows us to convert an alkene to the more substituted alcohol. So it's similar to acid catalyzed hydration, but the mechanism and the reagents are distinct, and in some cases the outcomes are different when you can have carbocation rearrangements. And so I'll mention that at the end. But this is what we call a two-step process. And so we're going to start with our alkene. We're going to treat with a mercury salt and water, and that's going to form a discrete intermediate that we refer to as an organomercury complex. And then in the second step, we're going to reduce that complex to get rid of the mercury. Okay, and so for a generic alkene, we're going to treat that alkene with mercury acetate. And so this is mercury 2 and water. Okay. And in that first step, so this will be step 1. We're going to generate that organomercury intermediate. So the structure will look something like this. Okay. And so I've added an OH and the mercury to the pi bond of the alkene. All right. And I threw an abbreviation here, AC. So AC is this, stands for acetyl. Okay. Which is that carbonyl plus the methyl group. We use that. It's a very common substituent. We use it so we don't have to draw it out all the time. Okay. So the product of step 1 is an organomercury intermediate. Okay. And you will isolate that compound. Okay. The organomercury intermediates themselves are not what we want. We want to get rid of the mercury. And so in a second step, then we're going to treat with a reagent known as sodium borohydride. So okay, that reagent there. And it's usually run under basic conditions. So you add aqueous sodium hydroxide to the reaction. Okay. And the sodium borohydride essentially is a source of H minus. And in this transformation, it replaces, the hydride will replace the mercury substituent on your molecule. And so we end up with a structure like that. All right. And so this is step 2. Let me write that down. Okay. So when you're drawing out these reactions, if we're not asking for mechanisms specifically, and you just want to invoke this transformation, there's a shorthand that you can draw, which is to essentially put both transformations over a single arrow. So okay, so that is a perfectly acceptable way to describe this reaction without having to draw out the organomercury intermediate. And so what is the mechanism of this transformation? Let me draw that on the next slide.
Quick question, what is THF?
Yes, sorry. THF is tetrahydrofuran. Which is that molecule there. And it's a it's just a common organic solvent that we use in the laboratory. And it's often employed, when we do these reactions. It's a nice polar aprotic solvent, relatively non-toxic, inexpensive. Okay, so, all right, so mechanism. So the first step involves reaction of the alkene with the mercury 2 salt. And this is analogous to what we saw on Monday in the reaction of an alkene with Br2. So okay. So I'm going to take the pi bonds from the alkene and have them attack the mercury. Okay. And so I can draw an arrow like this. And then I need to break one of the mercury acetate bonds. So I take the electrons in one of those bonds, doesn't matter which one, push them to the acetate. And then I'm going to take the electrons on mercury and push them back to the carbon on the alkene. Okay. And so we went through this, this is an unusual step because we've got 3 arrows. It looks a little confusing. We went through this step by step on Monday. And it's the pathway is identical to what we drew on Monday. So if you want to see it unpacked, I'd refer you to Monday's lecture. Okay. And so that's the initial product, or I should say product, it's an intermediate in this transformation. And this has a special name, which is called a mercurinium ion. Okay. And we lose acetate from the mercury in that step as well. And so we also have water around. And so water is going to trap that mercurinium ion by nucleophilic attack at the more substituted position. So I can take electrons, pick a lone pair on oxygen, start an arrow there, have that come up and attack, and then open the mercurinium ion. Okay. And that gets me to this species. Okay. And I still have acetate in solution. Okay. And the final step then involves an acid-base reaction where I transfer that proton on the oxygen in the product to acetate. So I can take a lone pair on my acetate and have that come over, pick up the proton, push electrons down. That neutralizes the product, and so you wind up with your organomercury intermediate. Plus acetic acid. Okay. So, again, always useful to reflect on pKa's for a second. And so does anyone know the pK of acetic acid?
Isn't it like 5 something?
Yeah, you're close. I mean, you're close enough, 4.76. Okay. And does anyone want to estimate the pKa of the protonated intermediate that I'm pointing with the blue arrow?
2.5.
Yeah, so lower. So hydronium, so H3O plus is about minus 1.7, right? And so this is going to be in that ballpark range. So let's call it -2. We'll say -2 to -1, somewhere in that range. Exact number is not as important. The point is, it's an acid-base reaction. You can look at these things as a competition between two bases for a proton. The stronger base wins. In this case, the stronger base is acetate. And we know it's a stronger base because the conjugate acid, acetic acid, has a higher pKa value. Okay. All right. So that concludes step one. So you make your organomercury intermediate. As I said, you don't want the mercury in there. We want to get rid of it. And so step two is going to be treatment with borohydride. And let me color code again here. So we've got hydride on boron. And if we can follow those hydrides, what we'd find is that they end up at the terminal position in the product. Okay. And so we are not going to worry about mechanism. So okay, we're not going to concern ourselves with the mechanism. Again, it's complicated. It's thought that what's known as free radicals are involved, and those are carbons with 7 electrons around them. It's not really that significant for what we're trying to teach here. So just know that if you take these organomercury intermediates, treat them with borohydride and base, you replace the mercury with a hydride from the sodium borohydride. Okay. All right. So that's the end of the new material for this class. And so what I'd like to do is now take the rest of the time to try and draw some similarities among the different reactions that you've seen to sort of help you, in organizing the information before we do that, I'll just pause and take any questions on the oxymercuration reduction.
What was the name of the beginning molecule that we reacted with the alkene? I think I just missed that.
This guy here?
Yeah.
Yep. Mercury acetate.
Okay, thank you.
Mm-hmm. All right, if there's no other questions, then I'll move on. So what I want you to do is to see as much as possible the parallels between the different reactions that we're talking about, the mechanistic parallels. It's very important. You know, I don't, my grad students, my postdocs, we don't memorize every reaction. We always think by analogy. And to the extent that you have a strong grounding in mechanism and structure, it's much easier to sort of extend that in different directions as needed without, you know, sort of, you know, resorting to cataloging everything independently. So first thing I want to do is point out the similarities between the mercurinium and bromonium ions. So okay. So when we first talked about the bromonium ion, I said that this was an example of a three atom, 4 electron type of system. So we can generalize that by just putting an X group there. Okay. And so there are 3 atoms involved and then 4 electrons. And when the 4 electrons I'm referring to are the 2 electrons here and the 2 electrons there. Okay. And so the mercurinium and bromonium ions are specific examples of this type of system. So you can just redraw those here. Okay. And an important point is that the positive charge in those ions is delocalized across the 3 atoms. Okay. So let me write this out explicitly. So okay. So on the left, we've got the bromonium ion. On the right, we've got a carbocation. Okay. the formal positive charge on bromine within the bromonium ion is going to be a more stable arrangement than having a situation where you have a bona fide carbocation, okay? And we can connect this with resonance structures that we talked about earlier in the class. So all right, so this is more stable. Okay, so if I put up this type of example, carbocation attached to oxygen, I can draw a resonance structure where I take a lone pair on oxygen and push them down, all right? And what I end up with is this structure on the right, okay? And so if I, sort of now analyze these structures, what I find on the left is that the carbocation, that carbon, lacks an octet. The structure on the right, all the atoms have an octet. And sort of goes hand in hand with this. I've maximized the bonding, right? So I've got two bonds between carbon and oxygen on the right, one on the left. Okay, so this is the more significant structure, and this one is less significant. Okay, another way to say that is that the structure on the right is expected to be more stable than the structure on the left. Obviously, it's important to remember we're not talking about an equilibrium. These are sort of contributors to the overall structure of the molecule. But the more stable structure, the structure with the more stable elements, contributes in a more significant way. Okay. Hopefully you see the analogy to the bromonium ion or the mercurium ion versus a carbocation. So in the bromonium ion, I've maximized bonding. I've filled the octet of the carbon, okay? And in a carbocation, I have an electron deficient carbon that only has 6 electrons around it. So it has a full positive charge. And so that is a less stable arrangement, okay? And so for this reason, what we say is that when you add the mercury or bromine to an alkene, you do not generate discrete carbocationic intermediates. So okay. So in other words, the addition of mercuric acetate to an alkene always forms that mercurinium ion. Okay. The corresponding carbocation is not formed. Okay. And so we have these sort of unusual three-membered rings that we're now generating. And okay, so I'm going to sort of talk about the positive charge that is there. So in the first step, when the alkene attacks the mercury, acetate leaves with the negative charge. So it's taking the electrons in the mercury-oxygen bond. So the system as a whole is still electron deficient, right? Even though I don't have a certified carbocation, okay? If you work out the formal charges on mercury, you should get to +1 as we've drawn there, okay? And we said that this is a better situation than a carbocation itself because I've maximized bonding and I filled all the octets, okay? Nonetheless, the mercurinium ion and the bromonium ion are still electron deficient, and the positive charge that we draw on mercury is simply a formal charge to help us with electron sort of bookkeeping, keeping track of the electrons, okay? But there's positive charge character delocalized over the mercury and the 2 carbons that are in the ring. So okay. And so we can show this with resonance, all right? And again, this is a little bit sort of going out on a limb with the, pushing the boundaries of what's legal with resonance. But I think it's helpful to see what's going on. And in these resonance structures, we're going to draw carbocations, but remember, we're not talking about equilibria. We're not proposing that a certified carbocation is formed. We're saying that there are these resonance structures that show us that overall, I have some positive character on carbon, okay? So let me draw that. Draw it in the middle here. Let's see why. Okay, so one structure that I can draw is to cleave this bond here, push the electrons up to mercury, call that path A. And the product then is this. Okay, and then the second structure is to cleave the alternate bond, call that path B, and get to this type of intermediate. Okay, call this one A, call this one capital B, okay? And just to drive home the point, because I know someone's going to ask me about this, A and B are not discrete carbocations. They are resonant structures of the mercurinium ion, okay? Okay, so those two structures show us that each of the carbons bears some positive character. Okay. But again, in the same way that you weight resonance structures, you know, for as we did when we learned about resonance, we can weight these structures, and the structure in the center is far and away the most significant because I've got a full octet and I've maximized bonding. And so the mercurinium ion looks most like the structure in the center. Okay, let me see if I can cut and paste this to the next put this on the next slide here. Copy this. All right, maybe not. I'll just redraw it. Let me redraw those on the next page. So we said this one on the left was A, the one on the right was B, okay? And so the mercurinium ion looks most like the structure in the center, right? Based on resonance considerations, we say that that structure contributes most significantly to the overall structure of the molecule. But A and B play a role, and they show us that the carbons have positive character. And the reason I go through all this is because A and B are not equal, right? They do not contribute equally to the overall structure of the mercurinium ion. Does anyone want to venture a guess as to which structure is more important or more significant?
Is it A?
A, correct. Why?
It's a secondary carbocation versus B, which would be a primary carbocation, which is less stable.
Excellent. Yep. Perfect. Sydney said it. A, secondary cation, going to be happier than B, primary cation. Okay. So okay. So A and B contribute less than the structure in the middle. And then within A and B, A is within A and B, A is the more significant structure, more substituted carbocation.
Sorry, what does it say after contribute?
A and B contribute less than the structure in the center to the overall structure.
Oh, okay, less than.
Yeah. This is why, honestly, I don't I type all the time. I don't, because I can't even go back and read my own handwriting after a week. So, all right. Again, I'm just going to say it one last time. We're not talking about an equilibria. You don't generate discrete carbocations. These resonance structures are just drawn to help us see that there's some cationic character on the carbons, okay? And because, we don't want to be drawing these cations, I don't want to confuse you. We're going to introduce a notation to show this. And the notation hopefully is unambiguous. And it's something like that, okay? So I draw the 3-membered mercurinium ion resonance structure, and then I write delta plus on the less hindered carbon, less substituted carbon, and then delta delta plus on the more substituted carbon, okay? And so this is a concise, unambiguous representation okay, of the structure, all right? And again, you might be thinking, okay, why is he spending so much time on this? The reason is that when the carbons are not equally substituted, you run into a complication, which is where is the oxygen of the water going to attack? And the answer is that it always attacks the carbon that has more positive character, okay? And so in that case, or in every case, it's going to be the more substituted carbon. So okay. Again, you can think about that in terms of electrostatics. I've got more electron deficiency at that carbon. As the water approaches, there's going to be more of that sort of, magnetic effect, electrostatic stabilization with the oxygen with the more at the more substituted position. Okay. And so if you remember when we talked about acid catalyzed hydration, so alkene plus sulfuric acid plus water goes to alcohol. We always said you protonate to form the more substituted carbocation. In that instance, then the water bonds to the more substituted carbon of the alkene. It's the same trend here. If I have an unsymmetrical alkene and I do the oxymercuration reduction, I always form the more substituted alcohol. The less substituted alcohol is never formed. Okay. And that selectivity derives from the mercurinium ion. Oops. I don't know if you guys, okay, the selectivity derives from the mercurinium ion there in the center, and that can be traced back to these different resonance structures, which tell us that the more substituted carbon has more positive character in that mercurinium ion, okay? So you may be wondering, how do you convert an alkene to the less substituted alcohol? And there's good chemistry to do that, known as hydroboration oxidation, which we'll talk about shortly. But you can't get there with the oxymercuration. The final thing that I want to point out is the consequences of the differences in mechanism between acid catalyzed hydration and oxymercuration reduction. So Okay, so they go through different intermediates. So the acid catalyzed process generates carbocation. The mercury mediated process does not. And so you may see where this is going. If I treat this alkene, for example, with sulfuric acid, I protonate to form a secondary carbocation. And let's do the color coding again. Okay. If I treat this alkene with mercury 2 and water, okay, I form mercurinium ion, okay, and water is going to attack this one to form that organomercury intermediate. Does anyone want to venture a guess as to what happens with this substrate on the left?
Are you gonna have a methyl shift?
Yep, you get a rearrangement. Remember, rearrangement's unimolecular process. Carbocation's very high in energy. If they can happen to get you to something more stable, it will. So this is a secondary cation. This is a tertiary. Okay. If this then traps water and you lose a proton, I'm skipping over the mechanism in the interest of time. You get to that product there. If you do the reduction of the organomercury, you get to that product on the right. So those are different products, obviously. And so the point is that you don't get rearrangements in the oxymercuration-reduction process. The reason is that you don't go through a discrete carbocation. And so in instances where the molecules can rearrange, you know, you need to apply a little bit of resolution in terms of which process you select. Okay. All right, so I'll stop there. Any questions before we end the class?
I had a quick question on the last thing you drew on the left-hand side. Why is the H coming off of, should it be coming off of a C or should it be coming off of the middle carbon, if that makes sense?
I think I got that right. So we're going to protonate this alkene with the sulfuric, right?
Okay.
And I like to color code it so you can see where the protons are.
Yeah. Oh, is it basically, I think I may have misunderstood. There is an H coming off of the right-handed C, but it's it's not that H, if that makes sense.
There is an H.
Because the C on the right hand, the middle C on the right hand side, the C at the I guess the 3 position would be would have a CH3, a CH3, and an H coming off of it. But the H coming off of it is different from the blue H.
Yeah, so this one has an H.
Okay.
Does that?
Yeah, I think
And then
I think what
there's 2 here.
Okay.
So if I draw them in the, I don't know if that clarifies it, Caroline.
Yeah, that does. I think I was just like, why is there not a charge or something? But it's basically because the H is bonding to the CH2 rather than a C.
Yeah. Sorry. Yeah, it's kind of this is the result of combination of, shorthand, my shorthand, and, sort of, yeah, more formalized stuff. Yeah, if you just imagine that there's the CH2s that are in the substrate I'm not explicitly drawing,
Okay.
Then it should work out that everything's neutral.
Okay, and the H from the H2SO4 is bonding to the CH2 rather than bonding to the C of the the middle part.
Yep, because remember, I could do that, but that would generate a primary cation.
Carbocation, which would not be as
Which is
stable.
going to be
Okay.
less stable. So always protonate the alkene so that you make the more stable cation.
Okay.
Yeah.
Thank you so much, Professor Herzon.
Yep. Any other questions? All right, if not, this will wrap it up. I'm going to take a 5-minute break, and then I'll come back and we'll have office hours. Okay. All right, I'll see everyone on Friday. Enjoy the rest of your week. Hope it goes well.